Okay. The first method is the zero shear viscosity method. Now, what is this zero shear viscosity method? If you recollect the picture that we saw in the earlier slide, the viscosity was varying in this particular way. So, this is zero shear viscosity, this is the infinite shear rate viscosity, and what you saw here was the non-Newtonian shear thinning regime. Okay. So, now we will be worried about using this particular value here. So, we will do a shear rate sweep, we use a rotational viscometer and we are going to use 120, 135 and 165 degree centigrade, and we will use a cross Williamson model. And then what we will do is use the calibrate the model parameters for this particular temperatures, and then what we will do, we will find out the viscosity for a shear rate of 0.001 reciprocal seconds. This is can be taken as the close to the zero shear rate, that because this seems to be the lowest shear rate that one can think of, and we then plot viscosity as a function of temperature. So, we find out the model parameters separately for 120 degree centigrade, 135 degree centigrade, 165 degree centigrade, and then we plot, estimate the viscosity at each of this for 0.001 reciprocal seconds, and then we plot viscosity as a function of temperature, and then whatever is the shear rate, whatever is the temperature that gives us 3 Pascal second is taken as mixing and 6 Pascal second is taken as the compaction temperature, right. So, this is for the first method is concerned. Now, let us take a look at the second method. Okay, I am basically discussing only the methods. The details associated with using a specific model, using data to calibrate and finding out is basically outside the scope, because you need to have some understanding of how to use a non-Newtonian fluid model, find out what are the parameters, use appropriate algorithms, maybe try to use MATLAB, and then find out the parameters and use these parameters to compute viscosity, and then plot viscosity as a function of temperature. If some of you are interested, you should always get in touch with one of us and we should be able to provide you separate worksheets towards the same. But as of now, what I have going to do is to explain the procedure that is necessary for you. The second one is the high shear rate viscosity. So, here you are going to do a shear rate sweep at 0.1 to 93 reciprocal seconds. We are going to use a rotational viscometer and you will conduct this test at 135 and 165 degree centigrade, and you use a inverse power law model. So, then using this inverse power law model and using the experimental data that is collected at 135 and 165 degree centigrade, you will find out the model parameters and then find out what is the viscosity as a function of using this 490 reciprocal seconds. So, as per the procedure that has been prescribed, this could be taken as the shear rate corresponding to the eta infinity. Now, you can actually ask this question as to why can't we really measure the viscosity at this particular shear rate. Similarly, you can always ask this question, why can't we really measure the viscosity at this particular 0.001. We need to understand that there are always the torque limits. The torque limits for any equipment are prescribed in terms of the low to the high. So, that means at very low torque levels, the measurements that you are going to make in any viscometer cannot really be considered reliable, and the same goes for torque limits that you consider at the highest. Normally for a rotational viscometer, if you make any measurement in the range of 10 to 90% of the capacity, torque capacity, these measurements are found to be reliable. Any measurement that is made below 10% or above 90% cannot be considered reliable, and there are some issues related to the calibration factors that are being used, and again we will not get into the details because this is something to do with measurement of the non-Newtonian response of the material using different measurement geometries and equipments, and that will kind of take the discussion out of the focus of this particular talk, right. So, you have 10 to 90% is the torque range here. So, if we have to make some measurements, and since we are talking about high shear rate viscosity, the high shear rate viscosity here prescribed is 490 reciprocal second. So, if it is going to be 490 reciprocal second, it is experimentally not possible to make any measurement of the viscosity for this particular using this particular equipment. So, what we are going to do is the following: we will make measurements from 0.1 to 93 reciprocal seconds. We use a inverse power law model. We then use the parameters of this power law model to find out what is the viscosity in 490 reciprocal seconds, and then we draw a viscosity versus temperature, and then wherever we get the temperature corresponding to 0.17 plus or minus 0.02 or 0.28 plus or minus 0.03 is taken as the mixing temperature or the compaction temperature. So, these two methods, which is the low shear rate, the previous one, which is the zero shear rate viscosity method, as well as the high shear rate viscosity method, uses the rotational viscometer. Now, we go to method 3, in which we are going to do what is called as the shear stress sweep experiments. So, here you are going to do a parallel plate assembly, and you are going to use a dynamic shear rheometer and this stress levels are going to vary from 0.16 to 500 pascals, and these are the temperatures that are prescribed. Now, if you recollect the discussion that we had when we talked about performance grading, you will realize that all these temperatures are performance grade temperatures, 58, 64, 70, 76, 82, 88 and 94 degrees centigrade. So, we need to run these experiments at these particular temperatures, basically do a shear stress sweep here, and what we are going to do is there is no model that is prescribed here. Okay. So, what we will do is to run an experiment, a shear stress sweep experiment in this particular way at each and every one of these temperatures, and then we will find out what is the viscosity at 500 pascals for each of these temperatures, plot viscosity as a function of temperature, extend this line. Okay. And wherever we get a viscosity temperature corresponding to 0.17 plus or minus 0.02 or 0.35 plus or minus 0.03 is typically taken as the mixing temperature as well as the compaction temperature. Now, you should understand some of the limitations here. What is the limitation here? We are measuring the response of the material from 76 to 94 degrees centigrade, and whatever viscosity that you are going to get from use for 500 pascal shear stress is extended, and that we are going to see what will be the temperature corresponding to this mixing and compaction temperature. So, but based on our preliminary discussion that we had at the start of the course, the response of the material starts at Newtonian, goes to non-Newtonian, goes to the viscoelastic regime as well as to the elastic regime as a function of temperature. So, that means around 140 or 150, 130 to 150 or above, you are going to be having a Newtonian regime. somewhere between 80 and 90 to 120, 130 it is going to be a shear thinning non-Newtonian regime, and then from 80 all the way up to 10 degrees centigrade it is going to be a viscoelastic regime, and again there is going to be a viscoelastic solid or a viscoelastic fluid regime, and below minus 10 degrees centigrade you are going to see the response of the material something like that of an elastic response. Now, what exactly is the problem? By this time you should have understood. We are making measurements in the viscoelastic regime and we are extending it to the non-Newtonian regime to try and see whether one could get some measure of the mixing and compaction temperature. This may work, this may not work, but as of now this is one of the methods that are prescribed here. And the fourth one, for which some amount of data is available and which more or less is being tried out at many places. Please understand, I am using the word tried out because even now in most of the places the manufacturer recommended mixing and compaction temperature is being used. So, in this method what we do is we use a DSR, parallel plate assembly, and then we do a frequency sweep. So, what is a frequency sweep? We start from the lowest frequency and let us say this is 0.001 and this is 100 radians per second. So, we do a sweep, right. So, that is what we do here, and we use a 1 mm gap here, and we do it in a, we do not now follow the PG temperature, but we just pick 50, 60, 70 and 80 degrees centigrade, and for these temperatures we fit a phase angle master curve, and by this time you should be aware of what exactly is a phase angle master curve. So, how do you think the phase angle master curve will vary as a function of reduced frequency? So, if you are talking about phase angle like this and this is going to be the reduced frequency, what will really happen at very high frequencies the phase angle is going to be close to almost close. So, it might vary in many ways, we do not yet know how it will vary, it all depends on the binder. So, at very high frequencies the phase angle is going to reduce, and we have discussed in earlier lectures by Professor Padma about plotting master curves. So, we plot a phase angle master curve, right, and then what we do now, once we have a master curve, what is the purpose of having a master curve? The purpose of having a master curve is to find out the material modulus at any other temperature and any other frequency over and above to whatever we have measured here, right. So, how do we go about doing it? So, let us say we want to find out the response of the material at 65 degrees centigrade, let us say for 50 radians per second. How do we do it? You are aware of the shift factor. So, what you will do? You will find out what is the shift factor corresponding to the temperature, and then knowing that shift factor you will use it to find out to compute the reduced frequency for any given frequency, and from the reduced frequency you will read it from this graph to get the actual phase angle. Now, what we are going to do is we will plot the master curve and this reduced frequency at a phase angle of 86 degree will be taken. Okay. Now, why is this 86 degree? 86 degree more or less is when the material is going to be Newtonian. Okay. Now, there is a small hitch here. 80, in fact, if you take a measure for the bituminous binder even at 80 degrees centigrade at very low frequencies, you might get a phase angle which is close to 86 degrees centigrade, but that is not really the point here. As we have discussed in our viscoelasticity lecture, as the phase angle goes to 90 degree, the response of the material is linearly viscous. So, we take this 86 degree frequency and then we substitute in this empirical expression. So, you see that there is a mixing temperature given by 325 times the frequency to the power minus 0.0135. Similarly, the compaction temperature is given. So, we use this and then we compute what is the mixing temperature. Of course, this will be given in degree Fahrenheit. In India, we have to appropriately convert it into degree centigrade. So, this is the method 4 here, right. And we actually at IIT Madras, and in fact with Dr. Nivita, Dr. Padma and a few others, we have tried to establish some test procedures for finding out the Newtonian non-Newtonian transition. If you are really interested, you can always go take a look at this particular paper published in Road Materials and Pavement Design, in which Dr. Nivita was able to characterize the rheological response of the material from in unmodified and modified bitumen in a wide range of temperature 90 to 200 degrees centigrade. These things are characterized. Okay. Now, how did we actually do it? We came out with a completely different way of looking at this. For instance, most of the procedures here talk only in terms of this shear rate sweep. When that means you do a pre-shearing for some time, and you can actually see in the y axis is the spindle and in the x axis is the time. So, you typically do a shear rate sweep with an increment as prescribed like this. So, if the response of the material is non-Newtonian, when you plot viscosity versus shear rate, you are going to get the appropriate data for use in a non-Newtonian fluid model. But what really happens during the mixing, during the compaction process? As the mixture is dumped in the field and as it is subjected to compaction using your compaction rollers, many things happens. One is the temperature of the mat substantially starts reducing, that is number 1. Number 2 is the mixture is being subjected to substantially high amount of shearing due to the roller compaction. We know very well that during the rolling operation, when it is subjected to very high shear rate, the binder can actually shear thin because of the non-Newtonian behavior of the material. But then the temperature also reduces and it can, the viscosity can increase. So, we have to find out a way of understanding these two contradictory things that are happening. Viscosity reducing because of the shear thinning behavior and viscosity that is increasing because of the temperature reduction. So, the actual compaction process that you see here is fairly complex, and unless one develops a test procedure, experimental test procedure in which one can bring in all these features, it is not really possible to measure what is really called as the actual mixing and compaction temperature. For instance, this particular procedure that you see here, we not only vary the temperature, we also vary the shear rate, and we get an interesting data for computing the Newtonian and non-Newtonian transition. In addition to this, there are also some steady shear protocols that are followed in similar to what is mentioned in the ASTM D4402 standard. So, basically we apply a steady shear rate and then we find out how the viscosity is varying as a function of shear rate for the different shear rates to which we subjected to. So, the idea is, this is, I just wanted to discuss this with you because this is some of the cutting edge that we need to do, and ultimately we are really looking at finding a very simple procedure for finding out the mixing and compaction temperature of modified binders. As far as unmodified binders are concerned, the rich amount of the empirical data that is available in the field tells us what we should do. But when it comes to the modified binder, there seems to be always an issue in finding it out, and most of the time what we do is we actually go by the manufacturer's advice, and most of the time it will be depending on the capacity of our hot mix plant as well as the construction machinery that we use, we add 15 to 20 degrees centigrade and we do it. But whether it will result in an appropriate development of an aggregate skeleton, or whether the beneficial effects of the modified binders will be truly mobilized during that construction is something we all need to know, and this is the more or less the issue throughout the world. Okay. So, first and foremost thing, if we really want to understand something about the mixing and compaction temperature, is we should understand non-Newtonian behavior. We really cannot get out of the fact that the response of the material during the mixing to compaction, roller compaction, is a Newtonian, non-Newtonian transition. So, we need to understand such transition. Number 2, this is the first one. The second one is, we also need to understand what exactly is the shear rate, or rather the distribution of it in the mixing and compaction regime. Okay, how much is the shear rate distribution? It is not enough if you find out the non-Newtonian behavior. Unless we know the shear rate, it is not going to be possible to effectively use this information, and we should understand what is the model to be used. Only then we can do. Then we also need to understand something about what is really called as workability or compactability. In recent times, where substantial amount of construction is going on of warm mix asphalt, half warm mix asphalt, or cold mix, with wrap, without wrap, we do not yet know how much is the compaction energy that has to be applied. Whether some of the mix can be or compactable or not is something that we need to really understand. So, it has something to do with workability and compactability, and in fact, in some of the IRC documents related to warm mix asphalt, few empirical measures have been already prescribed. Okay, you may want to find it out. And we also need to understand what is the influence of the mixing and compaction on the mechanical properties. For instance, we spend lot of money in trying to get a modified binder, but if the mixing and compaction have not really been carried out to the required rigor, and whether this beneficial effect that one expects using a modified binder, will it be transferred to the improved mechanical properties of the mixture, is something debatable. So, we need to really understand what exactly is the influence, and in many of the cases it was found out that because of poor construction practices related to mixing and compaction temperatures, very good modified binders which have proven to work very well, have not been able to showcase their improved mechanical performance, just because the compaction has not really been done very carefully. And so, when we have these kind of mixes, it is always necessary to find out these things, right. So, let us quickly summarize what we have been trying to do in this lecture for mixing and compaction temperatures. So, we had an outline of what happens during mixing and compaction. Then we talked about laboratory compactors. Here we showed gyratory as well as shear box compactors. Then we had a quick review of viscosity corresponding to mixing and compaction for unmodified binders, and then we said when modified binders are used, we realized that these procedures may not really work, and to understand how to prescribe this mixing and compaction temperatures for modified binder, we realized that we need to know little bit about non-Newtonian fluid mechanics. In fact, we did not spend any time on it, we only showed few models, the cross model, the 4 parameter model, and of course, the power law model. Then we listed 4 methods for for determining mixing and compaction temperatures. The first two method 1 and 2 used rotational viscometer. The first method talked about zero shear viscosity, the second method talked about high shear rate viscosity, and an appropriate model was used, and using the model parameters viscosity versus temperature charts were prepared, and from that the temperature corresponding to a specified viscosity was chosen. The method 3 and 4 used DSR, and this measurements, the measurements that using DSR, basically the first method 3 did not use any model, whereas in the method 4 the phase angle master curve was constructed, and using the frequency corresponding to 86-degree phase angle, one was able to find out the corresponding reduced frequency, which was used in an empirical expression to find out the mixing as well as the compaction temperature. We also discussed the various issues. Okay. So, this more or less concludes our discussion on mixing and compaction temperature for modified and unmodified binders. Thank you very much.